There are a number of interesting identities for the Fibonacci sequence that can probably best be understood using a matrix point of view. In this section, we're going to look at the generating matrix for the Fibonacci sequence. We'll extend it to negative indices. We'll look at the what I call the determinant relationship for the Fibonacci numbers. We'll show that consecutive Fibonacci numbers are relatively prime. And then we'll once again derive the formula for the nth Fibonacci number that we saw last time, this time using matrices. So here's our Fibonacci sequence. And let's start by extending it into a negative index region. So I think of one term being the difference of the two terms after it. So if we write, these are our first few terms here, and I want to go to the previous term, I'll go 1 minus 0, which is 1, 0 minus 1, 1 minus the negative 1 to get 2, negative 1 minus 2, 2 minus the negative 3, negative 3 minus 5, and what you see coming out is the alternating Fibonacci numbers going in this direction. So we will just write that sequence like this. F0, F negative 1, F negative 2, blah, 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 is the alternating Fibonacci numbers. Okay, now let's bring in the what I call the generated matrix for the Fibonacci sequence. Let's let A be this matrix, 0, 1, 1, 1, a 2 by 2 matrix. And I claim that if I take that matrix and I raise it to the nth power, I get a matrix full of Fibonacci numbers. Fn minus 1, Fn, Fn, and Fn plus 1. So for instance, a to the first power, according to this formula, should be F0, which is 1, F1, no, F0, which is 0, F1, which is 1, F1 is 1 here, and F2 is 1 right there. So we have agreement when n equals 1. So now let's prove this formula holds by induction. So the base case n equals 1 we just saw. So suppose it is true for a given n. And then consider n plus 1. So I look at a to the n plus 1 power being a to the n times a. And so I'm given that a to the n is this matrix. And then I multiply it by the generated matrix A. And what do we get? So in the first row, first column position, I'm getting Fn. First row times second column, I'm getting the sum. Second row, first column, I'm getting Fn plus 1. And second row, second column, I'm getting this sum. But these are Fibonacci numbers, and so we have sums of consecutive Fibonacci numbers. So this will be the n plus first. And down here we'll have the n plus second. QED. That's exactly the type of form we are looking for with n replaced with n plus 1. So now let's bring in the inverse matrix. So notice that A is invertible over Z. Its determinant is 0 minus 1, negative 1, which is a unit in the integers. And you'll recall the formula for A inverse. Of course, one can just multiply these out. But how do you get the inverse of any matrix? You take 1 over the determinant. And then we have to, for 2 by 2 matrices, we just switch the two diagonal entries and put negatives on the off diagonal entries. And then bringing the negative sign in, we get negative 1 +1, +1, and 0. And then you can show again by induction that for negative integers, that same matrix formula holds, just like we did for positive integers. Okay, the first relationship involving Fibonacci numbers that I want to prove is this. I call it the determinant relationship, and you'll see why I give it that name. For any integer n, the product of fn minus 1 and fn plus 1 minus the square of the nth Fibonacci number is -1 to the nth power. So here's our Fibonacci sequence. And let's just pause it at some place and look at these three terms, for instance. So if you take the product of the 5 and the 13 and you subtract the square of the number in the middle, it should always come out to be plus or minus 1. And in this case, we're getting 65 minus 64, which is plus 1. Or if we did the previous one, we would have 3 times 8 is 24 minus 25, that's -1. So we claim we always have this type of alternating behavior. Well, the easiest way to see this, and we're not going to need induction, is just to use the matrix. So this matrix A is 0, 1, 1, 1, and the determinant of A was -1. And then we saw that a to the n power is the matrix that has these entries. So if I look at the determinant of a to the n, that's just going to be exactly this expression on the left-hand side, fn minus 1, fn plus 1, minus fn squared. We also know that the determinant of a to the n power, this is a nice multiplicative property of determinants, is the determinant of a raised to the nth power, which is just -1 to the n. And so putting those two things together, we have proven the theorem. Now one can just do an induction proof of this identity, but it really wouldn't clue you in as to where has this identity come from in the first place. So I think this is a really neat way to think about it. Next, I claim that any two consecutive Fibonacci numbers are relatively prime. Any two consecutive are relatively prime. And this is going to be immediate from the relationship we just looked at. So we just proved this fact here. And let me just rewrite it like this. And what does this remind you of? So let's think of our two consecutive Fibonacci numbers being fn minus 1 and fn. And what do I see? I see a linear combination of fn minus 1 and fn equal to plus or minus 1. Therefore, these two numbers are relatively prime. QED. And that is, a typical consecutive pair of Fibonacci numbers. Okay, now let's rederive the formula we got for the nth Fibonacci numbers using a little linear algebra. So I start with our generated matrix A. The characteristic polynomial for A is defined to be the determinant of A minus lambda I. So take this matrix, subtract lambda times the identity, and form the determinant. And we get, let me just work that out over here, minus lambda, 1 minus lambda minus 1, which is lambda squared minus lambda minus 1. So the zeros of this quadratic are called the eigenvalues for the matrix A. And let's give those names phi and phi prime. And this is exactly the same equation we had last time. So phi is the golden ratio, and phi prime is its conjugate. 1 plus root 5 over 2 and 1 minus root 5 over 2. Okay, then we find the eigenvectors associated with these eigenvalues, and those are easily seen to be 1 comma phi and 1 comma phi prime. So I'll let you go ahead and do that calculation. And what did we learn in linear algebra is that once we have this set of eigenvalues and eigenvectors, we can diagonalize the matrix A, and we get the diagonalization P inverse A times P equals a diagonal matrix D, where the diagonal matrix has the eigenvalues along the main diagonal, and P is a matrix whose columns are the eigenvectors. So the best way to remember that connection is to rewrite this equation in this form. So here you're taking A, and think of this as being a matrix with column vectors, which are the eigenvectors, like this, a V1 and a V2 in the columns. And so A times V1 is your phi1 entry times V1, and A times V2 is the phi prime times V2. So that's where this type of relationship comes from. Okay, then we have P inverse AP is this diagonal matrix. I put the eigenvectors into these columns, 1 phi and 1 phi prime. The inverse, I again use the formula for the inverse of a 2 by 2 matrix, 1 over the determinant. Put the opposites on the diagonal and put these right here. Okay, the determinant is minus root 5, and that's why the negative signs are coming in here. And then rewrite this equation as A equals P D P inverse, which tells us that A to the n power is just A times A times A times A. And you've seen what happens when you do this type of product. You get all of these collapsing products in the middle, and all we're left with is a D to the n power sandwiched in between a P and P inverse. And now A to the n power is the matrix of Fibonacci numbers. This is your matrix P, and the 1 over root 5 is actually coming from the inverse matrix. I just pulled it over to the side. So you got P, D to the n power. This is a very easy calculation for a diagonal matrix. And this is your P inverse. And so multiplying it out and just picking out, say, this entry here, which is the first row, second column. So you take the first row and the second column here, and when we multiply that out, we'll get phi to the n minus phi prime to the n, and then the 1 over root 5, which is exactly the formula we ended up with last time.